Have you ever wondered how a character in a video game can run, jump, and flip all over the screen but still look exactly the same? Or how the pattern on a tiled floor just repeats perfectly? Well, that's not magic, it's geometry. Today, we are diving into the secret language of transformations, the rules that prove how shapes can be perfect copies of each other no matter where they end up.
Okay, so take a look at these two shapes. They look identical, right? Like perfect clones. But here's the thing. In math, just saying it looks the same doesn't cut it. That's not proof. The real question is, how can we describe the exact set of moves, the slide, the turn, or the flip, that would take one of these shapes and land it perfectly on top of the other? That is what we are here to figure out.
For example, let's look at square ABCD and square NPQR. To prove they're identical, we need a really precise language, a set of rules. It's all about finding that specific motion that connects them. We have to prove that one is just a repositioned version of the other.
So here's our game plan. First, we're going to define what identical really means in geometry. Then we'll build up our toolkit with 3 basic moves. After that, we'll see how to combine them for some more complex dances, uncover a really surprising secret about reflections, and finally, we'll wrap up with why any of this actually matters in the real world.
All right, let's jump into part 1. What makes shapes identical? Time to solve this clone conundrum.
The official term we're looking for here is congruent figures. Now, what's really important about this definition is that it's got 2 parts. It's not just that the shapes have to have the exact same size and shape. There also has to be something called a rigid motion that can map one onto the other. Just think of it like a move that doesn't stretch, shrink, or bend the shape in any way. It stays, well, rigid.
And it's actually pretty simple when you see it laid out like this. On the left, those shapes are congruent. You could literally pick one up and place it perfectly over the other. But on the right, they're not. I mean, they might be the same type of shape, but their sizes are different. So the key takeaway here is absolutely crucial. For congruence, you need the same size and the same shape, both.
So, if congruence is all about these rigid motions, what are they exactly? Well, let's move on to our next section and start building out our geometric toolkit.
Our very first move is called a translation. And honestly, it's just a fancy word for a slide. To get square ABCD to line up with NPQR, we just slide it 2 units to the left and 6 units down. No turning, no flipping, that's literally it.
Next up, we've got the reflection. You can just think of this one as a flip. See how triangle EFG is flipped over the x-axis to become triangle KLM? It's a perfect mirror image. If you could somehow fold the graph paper right on that x-axis, the 2 triangles would match up perfectly.
And our third and final tool is rotation, which is just a turn. Triangle HJI spins 180 degrees around the origin to become triangle STU. It's kind of like putting a pin right in the center of the graph and just spinning the triangle around it. So there you have it. Slide, flip, turn. That's translation, reflection, and rotation.
Okay, that's cool. But what happens when one move just isn't enough? Well, that brings us right to section 3, combining the moves. This is where we start describing the real dance of these shapes.
So when we start stringing these moves together, it gets a new name, a congruence transformation. Now, don't let the fancy term fool you. It's just the official name for a sequence of rigid motions. It's simply putting together the slides, flips, and turns that we've already learned.
Let's see how this works. How do we get this first parallelogram, ABCD, to map onto the second one, EFGH? Well, it's going to take 2 steps. First, we're going to reflect it across the y-axis. Then, we'll translate that new shape down. Okay, let's break down that first step. Just look at the original shape, ABCD. When we reflect it across that vertical y-axis, the new shape, we'll call it A', B', C', D', is now a perfect mirror image. See how its whole orientation has flipped? And from there, it's a straight shot. The orientation is correct now, so all we have to do is a simple translation. We just slide that new shape down 4 units, and voila! It lands perfectly on top of EFGH. So the full congruence transformation was a reflection followed by a translation.
Now for something really, really cool. It turns out that when you start combining reflections, some super predictable patterns start to show up. And that brings us to section 4, the secrets of reflection, or, as I like to call it, the power of 2.
So, what happens if you reflect a shape
and then you immediately reflect it again? Well, it all depends on the lines you're reflecting it over. If the lines are parallel, you get one result, but if the lines intersect, you get a completely different one. One creates a slide, and the other creates a turn. Let's see how that works.
This right here is the reflections in parallel lines theorem, and what it says is that reflecting a shape over two parallel lines gives you the exact same result as doing a single translation, or a slide. So basically, two flips equals one slide. Pretty neat, right?
And this theorem gives us an incredible shortcut. To find the total distance of the slide from G to G double prime, we don't even have to measure the slide itself. We just measure the distance between the two parallel lines, which is 9 plus 4, so 13, and then we just double it. The total distance is 26 units. It's as simple as that.
Okay, but what if the lines aren't parallel? What if they cross? Well, this is the reflections in intersecting lines theorem. It says that if you reflect a shape across two lines that cross each other, the result is actually a rotation. The whole shape will pivot around the exact point where those two lines intersect.
And just like before, there's another fantastic shortcut. The total angle of the rotation is exactly double the angle between those two intersecting lines. So in this diagram, the angle between the lines is 70 degrees. That means the total rotation from the original shape to the final one is just 2 times 70, which is 140 degrees. It's that predictable.
So, we've learned the moves, the combos, and even some secret rules. But why does any of this matter? In our final section, we're going to see that this idea of congruence is absolutely everywhere. Let's do a super quick recap of everything we covered. We learned that congruent figures are identical clones, same size, same shape. We proved this using 3 rigid motions: translation, which is a slide, reflection, a flip, and rotation, a turn. A sequence of these moves is called a congruence transformation. And we discovered that 2 reflections have a secret identity. They can create a single translation or a single rotation.
You know, this isn't just some abstract math concept. Congruence is like the hidden blueprint for our world. You see it in the repeating patterns of wallpaper, the perfect symmetry of a snowflake, and the amazing efficient structure of a honeycomb. All of these things are built on the simple rules of translation, reflection, and rotation. So, the next time you see a pattern out in the world, don't just see the shape. Try to see the motion. Ask yourself, was it a slide, a flip, or a turn that created the world you're looking at right now?